Okay, now let's go to control logics. In control logic, the instruction that we have for the counter is pretty the same. The only difference is about counter number. In rack-based PLCs, we do have counter number, while in tag-based, we need to define a tag. You can see that here. Instead of counter number, what we need to use here is tag. So we need to use the counter tag. If you remember, the counter number basically refers to the logical address that we are saving or we are storing the information of the counter. But here we don't need to deal with the logical address. We just use a tag and PLC processor will take care of the addressing part. So what you need to do in logic system, which is basically tag-based system, what you have to do is that you have to define a tag, which is your counter tag. So you need to create a tag. Let me show you here. So here, let's assume that we have this total tag. And the next step that you have to take care of is declaring the type of your tag that you have created. So if you're creating a tag for your counter, then the type needs to be a counter type. The other two parameters are similar to rack-based system. We do have preset and accumulator value. Now, if you want to address to the preset of this particular counter, for example, in a logic system, what you have to do is that you have to use the tag name. Here the tag name is total underline count. Now, if you want to address to the accumulator, you have to use .acc. And if you want to address to the preset value, you have to use .pre. So the addressing is exactly the same. The only difference is that instead of using the counter number, you have to use the counter tag. And if you want to address to any bit, you can use forward slash, for example, done bit or OV or whatever you want to address to. The other difference between these two parameters in logics and rack-based system is the size of the value that you can use for your accumulator and preset. So here the preset is 2 word and the accumulator is 2 word as well. So both of them are 2 words. And that means the maximum value that you can use for your preset and your accumulator is equal to 2 to the power of 31, because 2 word is equal to 32 bits. And you can see that here. So this is a much larger range for your preset and accumulator value. So that's another difference between the logic system and rack-based system. Okay, next part is about the application of counters. So I want to show you different application of counters. Let's start with turning on and off an output field device after a preset number of transition from false to true from the input signal. So let's assume that we have an input field device or input instruction, and based on how many transitions the counter can see from this input instruction, we want to turn on or turn off an output field device. So this is my counter. This can be a CTU or CTD. And then I have to use a counter number. Let's use C50, for example. And let's set the preset value to 10. Now, this is my input instruction. After 10 transition from false to true, the done bit of my counter will be equal to 1, and it can turn on an output field device. So if I use C5 0 colon 0 and then done bit, what happened is that my output 1 will be turned on. So as you can see, every transition from false to true will be detected by the counter. For example, at the end of this signal, I expect to have an accumulator value equal to 2 because I have 2 transition from false to true during this period. After detecting 10 transition from false to true, the done bit will turn to 1, and then the output 1 will be turned on. So this rung is showing me how I can turn on an output field device, turn on my output after 10 transition. Now, if I want to, let me use another color. Now, if I want to turn off an output field device after 10 transition, what I have to do is that still I have to use the done bit, but this time I have to use the close contact. So here I need to use this address, C5 0 done bit, and use this input instruction for output 2. So what will happen here is that I'm turning off an output after 10 transition. Now, if you need at some point to reset your accumulator value back to 0, you need to use a reset instruction. So you need to use a reset instruction with the same address as C5 colon 0. So let's assume that this is my reset switch. The color is really bad. So let's assume that this is what I have here is my reset switch, and whenever I need, based on my application, I can reset the accumulator value of this particular counter. Okay, so this is our first application. Let's review what happens here. So then I'll go to the second application. I want to tell you what is the difference between this first application and the second one that I'm going to discuss in a minute. So in the first application, my input field device, which is connected to this input instruction, is fed into my counter, is the input instruction of my counter. And based on how many transition the counter is looking at, it will turn on my output field device or turn off my output field device after 10 transition. But what happens next? After 10 transition, when the next transition is detected by my counter, what will happen is that the accumulator value will go up. So after 10th transition, if I receive another transition, then our ACC will go to 11. Sometimes we want to make sure that the accumulator value cannot exceed our preset value. That's our second case. So in first case, which we discussed in here, we don't care what happens to the accumulator value after it reaches to the preset. So after the accumulator value is equal to 10, we turn on the output field device because we know as soon as they are equal, we have a done bit equal to 1, so the output can be turned on or turned off after preset values of transition, but we don't care what happens to the accumulator value after that. If we want to make sure that the accumulator value cannot exceed the preset value, we need to add a little bit of modification to our program. Let's look at the program. So the second application is that I want to turn off, this is my second application. In my second application, I want to turn off my output field device or turn on my output field device after a preset number of transition of input signal, and I want to hold the accumulator value at preset when ACC is equal to preset. So when my accumulator value reaches to preset value, I want to make sure that it will remain there and it cannot go up to and exceed my preset value. What should I do? In this case, what I have to do, my program is going to be very much similar to the previous application. The difference is that after input instruction, I need to add the close contact of my done bit. So C5 0 / done bit here. And then I can have my counter. Let's assume that this is a CTU counter with the address of C5 0. And I'm using the done bit to turn on an output field device. So here I have C5 0 done bit. So this is, if I forget about this red part, my application is basically the copy of the previous application. But what happened here is that when the accumulator value is equal to my preset value, so as soon as those are equal, when I have accumulator value equal to preset, what happened is that the done bit will be 1, and obviously it turns on my output field device. But on the other hand, what will happen is that the continuity over this instruction will be interrupted. So before reaching to the preset value here, what I have here is an instruction which brings continuity all the time. But as soon as it reaches to 1, it reaches to preset value and turns my done bit to 1, the continuity over this instruction is interrupted, and my counter won't be able to see any transition here. You know that if I have a signal like this, and this signal is in series with this one, because they are in series, the result is going to be this. So my counter won't be able to see any of these transition anymore, so the accumulator value will remain equal to my preset value and it won't be greater than that anymore.